is about the application of Norwegian method of tunneling principles to Himalayan rocks with emphasis on rock support. And it's very nice to see that many of the principles have now been practically being applied in some of the tunnels in the Himalayas. And I really am happy to see, for example, RVNL, which has come to NGI and which is implementing some of these principles on the Himalayan rocks, and I hope that this will continue in the future. Now, we know that the construction of tunnels in anisotropic rocks, both weak and hard rock in the Himalayas, they have generated new thoughts in anticipating and assessing the problems posed by such rocks. And various case studies and observations have helped in a better comprehension of the existing problems. For example, squeezing ground. I recall in the earlier days when I was doing my PhD, so Dr. V.M. Sharma introduced me to Professor Ramurthy, Professor Bhavani Singh, and then Dr. R.K. Goel. So it was nice to see these case studies, and these have really helped us comprehend the problems in a good manner, because many of these tunnels were instrumented at that time, for example, from Dr. Jetwa and the others who have had considerable experience on squeezing ground conditions. So in this presentation, an attempt has been made to assess the applicability of NMT to Himalayan rocks. Now, many of you may ask, why NMT? Which is a very valid question. Why should we look into the Norwegian method of tunneling? Well, if you look at in Norway, many of our colleagues who have come here from India, they have seen that we have about 750 railway tunnels in Norway, 1,000 road tunnels, and 35 subsea tunnels, in total length of approximately 3,000 kilometers. And which, if you include the hydropower tunnels, so we have 7,000 kilometers of tunnels in Norway. So what we say is practically everyone in Norway owns a few meters of tunnels. So you can see here the statistics which shows how the tunneling has been going on since 1971 till now. And these days we have 7 million cubic meter of rock being excavated in Norway every year. And I'm very happy to note that India is also now constructing approximately, I think, about 100 kilometers a year, which Norway has been doing for the past 25 to 30 years. Now, some of the essential features of NMT have been described by Dr. Barton in 1992 and his recent publication in 2017. And I'll just go through some of these principles. And if some of you are interested in having these publications, then I will forward these publications to Dr. Bhasin or ISRMTT so that these can be forwarded to all those who are interested. Now, the essential features of NMT, it's most appropriate for jointed hard rocks and for weak rocks too. And as you know, it's the temporary support in the NMT technology is based on the rock mass classification. And we do carry out monitoring when deformation is expected. And basically, it's fiber reinforced straight concrete plus rock poles and reinforced ribs of shotcrete as temporary support. So this reinforced ribs of shotcrete, I'll come back to it later in my presentation. So this is the main support which is used, and the permanent support consists of the temporary support as described above, plus supplement and water shielding. So basically, what we say is it is a single shell technology. So we used basically NMT is single shell in contrast to the NATM, where you have for example, the lattice girders or other hard support, and then you have a final lining after that. And the NMT also includes the drainage, ventilation, plus illumination. And this is a very important figure, that the cost of tunnels in Norway, now since we are working on so many tunnels, so this I have also been talking to my colleagues, it's in between 10 to 15,000 USD per running meter of tunnel. So this is the cost of NMT these days too. So this is a the tunnels which we have been working on. And many of the tunnels, some of the examples which I will give later, the cost is probably even less. But now, due to the certain criterias which have come up in NMT, so the cost has gone up to 15,000 USD per running meter of tunnel for a two-way, you can see, approximately 10-meter span tunnel. Now, the important principles of NMT, we have to carry out site investigations, and usually we're using geophysical methods. And the application of updated Q system of rock mass classification to estimate the rock support. And we have evaluation of parameters related to rock jointing and shear resistance of joints, roughness, strength, permeability, aperture, etc. And then we convert this three-dimensional geological excavation into an idealized 2D model for numerical modeling. And then we integrate the empirical and the numerical approaches to validate rock support design. And then there's rapid advance of tunnel using modern excavation techniques, which I'll come back to show you later. So basically, the principles of NMT, they integrate the empirical and the numerical approaches, and these approaches will be subsequently described. And when we look at the overall benefits of Norwegian tunneling, so it's fast and safe construction at affordable costs, and it's time and cost efficient. And NMT adapts to the actual ground conditions to install suitable rock reinforcement based on the Q system. And then there are new regulations in construction contracts which allow the geologists half an hour for mapping and classification following each blast round. And the contractor may be reimbursed for possible hampering. So this is the new regulations which have come up. And the Norwegian tunneling is recognized by informal organization culture and fast decision making, wherein all parties respect each other. So these are the benefits of Norwegian tunneling. I thought that it'd be good to give these highlights right in the beginning before I go into the interesting parts later on. Now, the stepwise procedure for ground investigations that you can see here, there are basically three procedures. We have the pre-investigation, pre-construction stage, during construction, and then during operation. And in the pre-construction stage, we have the project conceptualization, where basically knowledge of the ground conditions is obtained. And then here we recognize the major challenges. And in the feasibility, we carry out desk study of aerial photographs, maps, reports, and visit to nearby locations. So this forms the basis for the preliminary design. And then we have the detailed investigations where we carry out engineering geological mapping, geophysical investigations, drilling, lab testing, etc., which constitutes the final design. And then during the construction, the tunnel mapping, probe drilling, monitoring, sampling, laboratory testing can be performed, where we modify the design if necessary. And then during the operation, we have the monitoring and quality control. So this is the stepwise procedure for ground investigation for tunnels. And here you see some of the investigations which we have carried out in the Himalayas. This is a photograph of airborne electromagnetic survey which we performed in Bhutan some time back. And you can see here that this is what we're doing is we're having this antenna which is about 250 square meters, and the basic purpose here is to find the resistivity of the bedrock. So we know that the resistivity of the bedrock can give you ideas whether the rock is competent or not, and this can be carried out, it's usually carried out about 30 meters above the tree line. And it can be carried out in any type of weather, whether there is snow or this. And you can see this is another example of the work which we carried out for a hydropower tunnel in Zambia. So this was also the geophysical investigations performed there. And this is just 3 weeks back that we carried out AEM for 4 tunnels in Ladakh. And as you know, Ladakh is one of the most considered as very important area due to its proximity to the border. So 4 tunnels are being planned here, and we carried out this for the Ministry of Transport, NHIDCL, and this work has been going on even during the COVID period. So we're able to map some areas, and so this was carried out in cooperation with the NHIDCL, the Indian Air Force, and the SkyTime, which was our subcontractor, and Ananjiwala, and then Emerald Geomodeling. This is just a small figure which shows what type of results can you expect from AEM. So here you can see the resistivity of the rock. So basically it can penetrate quite deep, 700 meters. So we know that high resistive areas, for example, areas where you have red color. So this here, high resistive areas, those areas are considered as competent rock, and then low resistivity areas are usually areas where there may be water fractures and where the rock may be conductive. So one can get an idea of the terrain or the subsurface geology using this new type of method, which we now frequently use in Norway and use also in other projects abroad, as I mentioned, in Ladakh or in Bhutan. Now the AEM has certain opportunities. It reduces the costs and extends the database. And the reason for that is that then the drillings may be avoided in many areas, because sometimes you have to drill very deep to find out the depth of bedrock. And when you do drilling, it's just like a point, you know, the conditions at a certain point. But with AEM technology, you'll be able to get a good idea of the bedrock and then align your tunnel accordingly. And you can fly almost everywhere. And as I mentioned earlier, the penetration depth can be up to 700 meters. And you have certain limitations for this AEM technology. And these can be applied to medium or large projects. So if you have a long tunnel, 10-15 kilometer long tunnel, then I think it's very good to apply this technology. And it's difficult to do this type of work in urban areas where you have electrical cables, because the measurements, the energy dissipates, and then you have a lot of noise coming. So this is not so easy to do in urban areas where there's a lot of infrastructure exists. And then we see that there is lateral resolution is probably better with the electrical resistive tomographic method. Now, after the feasibility studies, then we carry out the detailed investigations and we characterize the site using the Q system to evaluate joint rock parameters. And in this respect, I just want to emphasize the mechanical behavior of rock joints is very important. So please bear with me for a few more minutes concerning it might be a little bit theoretical, but I think it's very important to know that the mechanical behavior of rock joints is very important, especially when you're characterizing the rock mass and evaluating the properties. And we know that the mechanical behavior of jointed rock mass is strongly affected by the behavior of discontinuities. And this is especially true for underground and rock slope stability problems. Therefore, the joint constitutive models for discontinuities play an important part in the successful application of any numerical technique. And here you can see the difference between various models. And we at NGI, we're mostly applying the Barton-Bandis BB model, which is a non-linear model. And the Moore-Coulomb model, we know that it's a linear model and it's basically non-realistic, but due to the computational efficiency, we're always using the MC model because the parameters we can get from the literature. But I would like to emphasize that the BB model, the parameters are equally easy to obtain. And one more thing is that BB model, the properties here are scale dependent and are not dependent on the normal stress, as in the case of C and phi. So C and phi parameters, we know that there are scale effects and also normal stress dependent. So this is the key difference between the two joint constitutive models. And there are very simple index tests which I've just described to you to determine the joint roughness coefficient, the joint wall compressive strength, and the residual friction angle. And basically, we're using tilt test, profiling, and Schmidt-Hammer tests to find the various parameters, JRC, JCS, and residual friction angle. And you can see that here, that you can carry out simple tilt tests in the field. And if you have important projects, for example, in the design of nuclear-based repositories where you have a lot of cores, you can also use an apparatus to test the and get the friction angle of the joints. And you can do Schmidt-Hammer tests. I'm sure all of you are familiar with this. So this is also JCS values are easily obtained through that. And then you have the profilometer, where you're using the profilometer to get a profile of the joint to measure the joint roughness coefficient. So this JRC, JCS, and phi are very easily obtained. And I would say that it's a much more realistic model to use than the Moore-Coulomb model. And I'm not going to go into the detail, but these are just some of the formulations which you can read in the Barton and Chobe publication. So the use of BB model for rock joint modeling is quite realistic and very useful when we are trying to validate especially the rock reinforcement requirements in a tunnel. Now, this is the last figure which I'm going to show you about the BB model, I think, but I just wanted to point out that there are scale effects on the peak shear strength for various JRC, JC values. So what are the scale effects? So this is I just given an example. When the block size is 2 times larger than the laboratory size, we can see that the peak shear strength increases when the JRC value increases, which is understandable. When the block size, laboratory block size, when the field block size is 5 times larger than the laboratory, then also we see that the peak shear strength increases as the JRC value increases. You see here from 3.87 MPa here. But when the block size in the field is 10 times larger than the laboratory size, we see that the peak shear strength does not necessarily increase when you increase the JRC. And this is due to the large undulations which occur. So we feel that this model does take into account, it's a tested model, it's empirical, but it's really very good to use this model in a realistic, especially when you're using hydromechanical coupling in the numerical models. Now I'll be showing you some examples of integration of rock mechanical data in numerical analysis. And as Dr. Rajbhat Singh mentioned right in the beginning, that this was the world's largest man-made cavern for public use, Norway's Olympic Cavern, which was constructed in 1994. And as you know, the NMT word was coined by Dr. Barton and et al. In 1992. So this was the 62-meter span Olympic Cavern, where you had the pilot tunnel, the side stoping, and then you had the another access tunnel. And here you can see here that due to the construction methodology and the applicability of NMT, that we had rock bolts which were from 6 meters to 12 meters long for such a large construction. And I can inform you that during the I had the privilege of guiding Professor Herbert Einstein from MIT a few years back, and he was surprised to see that the rock moss quality was not that good. So he said, Rajinder, this rock moss quality is not very good, so I'm really surprised that you could build 62-meter span here. So I think it's, as I mentioned earlier, when you follow the principles which I have outlined earlier, and then you have skilled labor. So even such a big construction where the rock support is not that much, but it was done in a very systematic way. And for those who are interested in reading about this, there's a very nice article written by Dr. Barton in 1994 about the predicted and measured performance of the 62-meter span Olympic Cavern. This highlights many of the principles which were used, which I have described earlier. And those of you who are interested in about the engineering geological investigations and the application of rock mass classification approach, so this is another article which was in 1993. So this describes how the mapping was performed at that time. And as I said earlier, I'll make many of these publications available to to ISRMTT for those who are interested. And this stadium looks like this right now. It has a 6,000 seating capacity and 30,000 people can be inside. And this is just a view of the Olympic Hall. And you can see here the figure below, 30,000 people can be accommodated in this stadium. And it's just like a big hole in a mountain, you know. And as I mentioned earlier, that the numerical distinct element modeling was performed here with the excavation steps. And we had used the Barton-Bandis JRC JCS criterion, and some of the parameters are here. So I will not go into the detail, but this is described in that in those publications which I showed you earlier. And we had also carried out instrumentation both from inside the cavern and also from the surface. And this is another very interesting project which is coming up, and it's called the Start Ship Tunnel. And the reason for constructing this, or planning and constructing this tunnel, is that if you look into the west coast of Norway, if you look in this, you know, we know that Norway is not very far from England, and on the west coast, it's extremely windy, and several boats have capsized. And here, it's one of the touristic areas where people travel from the south to the north to see the midnight sun through this ferries. And this tunnel, which I said is planned right here to avoid this rough area. And it's called a Start Ship Tunnel. And you can see here that the sea is rough on the west coast. And as I mentioned here, several people have died long back and boats have capsized. So it's quite rough sea, and this tunnel is about 1.7 kilometers long. And basically you can say it's like a powerhouse, a 1.7 kilometer long powerhouse, which is there. And as I show here, 36 meter wide, 37 meter high, and the cross section is about 1,650 square meter. So this is that tunnel which is planned and has been approved by the parliament, but has not started construction. And some of the key features of this is that it has a length of 1,700 meters, and the height between the tunnel floor and ceiling is 50 meters. And I think I've given you these figures, and the total cost is about 2.7 billion kroner, which is like 303 to 400 million USD for this. And the anticipated construction time will be 3 to 4 years. And Mr. Grimstad had carried out surface mapping of this area earlier using the Q system, and he has distributed the Q values in percent, and based on that we were able to estimate the rock support and also the costs. And I had carried out this very quick analysis showing that what type of rock support would be needed. So this was the first initial very quick analysis. The detailed design has not been yet done. So this is 11 meter rock molds we tried, but we saw that the excavation disturbed zone is beyond that. And here we see that at least 14 meter long bolts are required. And the cross section, as I said here, is this, and the maximum deformation expected in the walls is 51 millimeter for the rock, for bad rock quality with Q is equal to 1. And in good rock quality, we expect the deformations to be less, about 16 millimeters. And what we're using is that the 15 meter long, 27 millimeter dia bolts are planned to be used there. And this is another project, which is Northern Europe's largest underground station. It's just outside the Oslo area. And this was also, this is a section of the cavern, which you can see here. It's 34.5 meter wide and 16 meter high. And in this tunnel, even though we had done some of the numerical modeling, but here the contractor opted to use lattice girders instead of the RRS, which is commonly applied. So which you can see here. So here also we have some publications for those who are interested in this, but the mapping was done with using the Q system, as I mentioned earlier. So basically, the more input you have, the more confidence we obtained, and this is very important. And one of the things which we have experienced is that for example, in India, in all the projects where we have been involved, we are not using up to 3 to 5% of the project costs for investigations. And I think that's one of the main reasons why we have most of the projects have cost overruns. So the expenditures for engineering geological investigations and site characterization should be at least 3 to 5%, so we gain confidence and we do a good design of the structures. And this has been lacking in many of the projects. I don't want to name the projects, but in the projects we have been involved. So I've heard from the clients that they have used 0.5%. And now in Norway, we're using significant amounts to do the verification and document support, especially during the planning of the projects. And this is just a figure showing the various different rock mass models, which one you can use based on your existing prevailing conditions in the ground. You can use the finite element, distinct element, or the hybrid approaches. And usually at NGI, I said we use the distinct element code. And this is an example of one of the work which I had carried out long back on a subsea tunnel, where we make the numerical model and then we construct the model, excavate the tunnel and see the deformations, and then we integrate these input parameters in the numerical model, and then we validate the support requirements. And basically what we're doing is we're saving money for the clients in that respect. So here, this is some of the examples, and there are several more examples where we optimize the rock support through numerical techniques. And this is an example from distinct element code using for a road tunnel in the Himalaya. And actually, basically, this was the Thimphu Wangdi tunnel, which we had investigated, where we had used all the NMT principles, which I have highlighted earlier, and the feasibility report is available with the Department of Geology and Mines in Bhutan on how we have carried out this study. And we also carried out some parametric studies for earthquake loading. And this diagram shows that both the displacement and the rock support are more affected by an earthquake for small overburden than deeper tunnels. So we see that this is basically the different rock mass qualities. The colors indicate different rock mass qualities, and the hashed is the earthquake loading which we apply. And we see that when the overburden is less than 200 meters, then there are more rock bolt failures and liner failures than when we go deeper into that. So this type of work is much more realistic when you do with distinct element modeling, because the rock support failures are much better modeled using that. And this is an example of an FEM displacement. This is a quick, you can say, FEM result, which shows that with an overburden of about 1000 meter, the displacement is about 5 millimeter for a Q value of 4 to 40. And then if you have very bad rock, then the displacement can be 30 millimeters. So for this just gives you an idea, but I think for details, you need to do this distinct element modeling for verifying the rock support. So the results of that study indicated that the recommended support should be based on the Q system, should be efficient to prevent instabilities in case of poor to better rock qualities. But for very poor to extremely poor rock qualities, the rock support needs to be strengthened when the overburden exceeds 1000 meters. And the numerical models are based on a certain number of assumptions that should be verified during the construction. And updating these models will help in better planning of the work and risks during construction. And We always estimate the rock support using the Q system. Most of you are familiar with this diagram, but we have experienced that in the Himalayas, still people have their own rock support, even though they're using the Q system, but the rock support systems recommended by this diagram are not being systematically followed. So this is just an example showing that how we are able to estimate the tunnel length for various Q values when we have done the mapping, and what should be the rock support, and then we have the unit costs, and then we calculate the total cost of the tunnel based on that. And such type of rock support, like steel ribs and concrete linings, are not at all used in Norway. So this type of heavy steel support with backlegging and fully concrete linings, they're not applied. Instead, we are using the RRS, and even in such rock mass quality which you see here, the rock mass quality here is quite poor. In such rock mass quality, which is obtained from a borehole, we're using the reinforced ribs of shotcrete. So here you can see that if you have this type of rock mass quality, then you know that RRS is applicable. And how does it look like? I think this is also, many of you are familiar with the reinforced ribs of shotcrete design, which you see here, how it's implemented. Basically, it has this 6 reinforcement of 20 millimeter diameters, and then you have the crossbars which are shown here, and then you have the rock bolts attached here. And this is a close-up figure of the same, which you see here, that you even out the surface with a shotcrete, and then you set up the RRS, then you apply the crossbars, and then you spray it over. So even if you have very bad rock quality where you have to do 4-poling, you can still apply the RRS. So here you see that 4 poles are there, and then you have the RRS reinforced ribs of shotcrete, which you see here, and then this person is now drilling to install the crossbars, which you see here right now. So he's installing those crossbars to keep everything in place. And then before spraying the ribs of shotcrete, we should have a water spray for obtaining good adhesion between the surface and the shotcrete. So this is very important. So this also takes just a couple of minutes, So after you've installed the RRS, what you do is you have clean the surface with a water spray before spraying the shotcrete, and then this will result in good adhesion. So this is what this person is doing now. And you can see here that after spraying the water, now shotcrete is being sprayed after the cleaning. So here you see, and then this is the finished product. So in Norway, all the tunnels right now, they are being built using this technique, and you have different formulations of RRS, and we have also instrumented these several RRS, and we have a new project where we're going to instrument even more RRS to obtain a better comprehension of the load which it can take, because right now we know that RRS has worked for certain type of rock qualities, but it's always good to have the quantitative figures of the load coming on that RRS. And we have earlier compared between numerical analysis, which you see here on the right, with the static load. So we have done considerable amount of work. In this case, you see here that these are the numerical simulations, and these are the with the static analysis. We see that it's quite similar, except the bending moments. And the reason for that is that when you do this static analysis, you have no confinement behind here. So of course the bending moment is much higher compared to the confinement which you have here. So there's also a publication on this for those who are interested. We can send that. And basically 3 different RRS configurations are chosen, which are described in the Q system handbook, which is the RRS 1, 2, and 3. And it explains here that the RRS 1 for rock quality between 0.1 and 0.4, here you can use a single rebar layer, which is 30 centimeter thick and 6 rebars. And RRS 2 is a double rebar layer, where the D stands for double, SI stands for single, and which means it's 45 centimeter thick, 6 with double layer of RRS, and then here the thickness is even more. So this is the RRS3. So 3 different RRS configurations can be chosen as described in the queue system. Now this is another example of an existing mountain road in the west of Norway, and I found that this is not much different from what we have experienced in the Himalayas, where we also plan a tunnel because these roads which are right here are usually blocked during the winter. So you see that this is one of the figures I took from the road above the Zojila Pass in Ladakh, where we have performed recently AEM. So this is the road which is continuously blocked, and that's why the tunnel is planned. And this is very similar to the Lardal tunnel, which is the 24.5 kilometer long tunnel, where the road, the original road was like this. So these two figures are quite similar, and it shows why we need these tunnels. And as I mentioned here earlier, that these for Zojila Pass, now the geology is probably better defined than before. And this is the world's longest road tunnel, 24.5 kilometer. And here also the NGI was the main geological consultant for the project. And this is one of the turnarounds of this cavern. So basically what we have in Norwegian road tunnels is that we have the scaled rock surface, that you do the scaling, you do the spraying of the concrete, which is shown here, and then you apply the rock bolts, and then you have the tunnel lining, which is basically a free element for water and frost protection. So this is the usual way, but of course I'm just explaining this in a very simple manner, but you have for bad rock conditions, then you're applying this RRS instead of the steel supports. So this tunnel, which is the world's longest road tunnel, it was 24 kilometer long there, and it's an important link of the road connecting the eastern and western part of southern Norway. And the tunnel goes through pre-Cambrian gneiss with a cover of 1,500 meters. And here you have major faults, and the maximum excavation per week per face was 108 meters on the face. And as I indicated earlier, that this was constructed 20 years ago, so the cost was less. It was 8,000 USD per running meter of that tunnel, which I just showed you for. So that was the cost using the NMT technology. So you have various Norwegian developed methods and equipment. I'm just going to show a figure of some of these equipments. You have this AMV, which stands for Andersen Mechanics Verksted. It is in the west of Norway, and the sprayed concrete robot, so which is commonly used here in Norway. And then you have the water sealing systems. So this is not the one which is prefabricated, but it's a system which is commonly used. And then you have the CT bolt, which is corrosion protected many times. And then you have also the D bolt, which can take these dynamic loads. So there are several publications relating to these methods and equipment for those who are interested. And then you have these truck mounted bolting rigs which are used. So here you can see the truck, and this is the bolting rig which is mounted on the truck, and it can be used for slope stability problems, or it can be used inside the tunnel where you see the person who's sitting here. So these are truck mounted bolting rigs produced in Norway by the same company which I had shown earlier, where we are using this NMT. Now, at the end, I just want to show that the projects which are related not only for civilian, but for also military purposes. So NMT has been used extensively in the west and north of Norway, and this is one of the naval facilities. It's not a good photograph, but it shows where ships and submarines can go in. So NMT has been used commonly in that, and this is one of the islands This is just a cross section which shows the island, where it's a multi-purpose facility for torpedoes and mines, because as I've showed you in the map, Norway is very close to Russia. So they have this facility there for safeguarding their territory. And just concentrate on this here. This is the facility where they have these torpedoes and mines, and we visited that. And in this, the boreholes have cables which are attached to the mines in the field. So this area which is shown here is right here. And to enter this facility, it's camouflaged. It just has a concrete small bunker where you go in, and then on the right hand side you can see that you go quite deep inside for this multi-purpose facility. And then you have the equipment, military equipment installations there. So it's these underground military purpose facilities. Many of these exist in Norway, especially in the north. And here's another one for storage purposes. And I think India is also planning many of these type of storage facilities in the future, where you have a big mountain which is cut off, and then you have the workshop here, you have the entrance here, and then you have some technical rooms, and then you have a depot for the heavy equipment and for vehicles. So this is just a section showing how the storage facilities. And this is a photograph inside. You can see the sealing system, water sealing system, and the military equipment. And here is the ammunition storages also. So these figures are from the Norwegian Defense Estates Agencies, so where these technologies have been used. So at the end, I would just like to again come back to the benefits of Norwegian method of tunneling. So as I mentioned here, it's fast and safe construction at affordable costs. It's both time and cost efficient. Q system based rock reinforcements, that's the key for the NMT technology. And regulations allow the geologists half an hour for mapping and classification following each blast round. So this is because as I said, NMT is based on the design as you go method. So these regulations allow the geologists for mapping and classification following each blast round to select the appropriate rock reinforcement. And then an informal organization culture and decision making exists where all parties respect each other. So this is also one of the important components. And last but not the least, NMT is much more environmentally friendly than any other technique due to the less use of concrete. So when you compare, for example, with NATM, where you have thick concrete elements, and here NMT, it's we use very little concrete as compared to, and we know that concrete is production of concrete or cement is a good source of CO2, so it's much more environmentally friendly. And so I would like to thank you for your attention and listening. And as I mentioned earlier, I will try to share all the publications for those who are interested with the ISRM team. Thank you very much.
Thank you very much, sir.